In our next topic, we're going to talk about line integrals. What are line integrals? We have already done a type of line integral, which is arc length. Just like, so if I had a path, I could stop between time A and time B. We've said we can compute the length of that curve if I have parameterized it in terms of t, and then I do what we called arc length. Arc length is the equivalent of having in double integrals and triple integrals of integrating the function 1, right? If I integrate the function 1 in a region in the plane, I get the area of that region. If I integrate the function 1 in a region in 3D, I get the volume of that region. If I integrate the function 1 against arc length, I get the length of the curve. But this curve might have a function on top, that there's a function that I want to sort of count and add values of that function along that path. For example, this piece of rope could be some cable that doesn't have the same type of density all along the cable, and I want to figure out what is the total density, the total mass of this piece of cable in this stretch. So there can be another function, something, let me just draw something sort of on top that goes up and down like this, and then there is some function that I'm sort of integrating along that path. Oh, that didn't come out right, but it's something like this. And then I'm doing an integral that is sort of like what you did in Calculus 1, except that this integral is going over a path that is not a line. It's not a line segment. Okay? So we want to do that kind of thing. And once again, the Riemann integral is the right person for the job because I can take first my path, I break it into subintervals, and then essentially, if there's a function that is being evaluated at all those points, what we can do is, well, just write boxes, essentially, of the appropriate heights, you know, whatever the function is doing, those points, and then as we decrease the subintervals in t, those points are going to be closer and closer together, and when you do the limit, you get what is called the integral. So you can see a better representation here graphically of what's happening when we do a Riemann integral over a path, and there is a function on top that we're integrating. So again, the integral, this integral is going to be, we're going to be integrating, and we are going to be integrated against what we call arc length. So that parameter is arc length. And arc length means that we are integrating essentially what we want is, let me give you a better sketch of what's happening. What would be the length from here to here of any one of those rectangles? If I want to compute the area of that rectangle over there, I also need to estimate what is this length, and what I'm going to estimate it is by the tangent vector at that point. And similarly, at every point, I need to estimate this length, so I'm going to estimate it by the tangent vector and the length of the tangent vector at that point. So times the distance between the points. So that is going to give me a measure of what is the length of those arcs. So each one of these arcs here are going to be estimated by the length of the, essentially that is what's going to be this parameter arc length. And when you just integrate at the end of the day in the Riemann integral, what you get is this. This is the length of the tangent vector times the space in t. So that is the function that we're integrating over the path times, and this whole piece is what we call arc length. This type of measure is what we usually just write ds for it. but it's the integral that you would get when you do an integral of arc length. Okay, so let me show you how this works by trying to compute integral of a function about one particular path. So we're going to integrate the function 2 plus x squared y. That is a function of xy. It has values in the entire plane. But we're only going to travel in the unit circle. So here is 1, and here is -1. And it's the upper half of the unit circle. So I want to just integrate above this unit circle. That function will have, I don't know, some shape like this above the unit circle. And that's sort of like the function, if I was going to stretch it out, it's going to be some integral in t between, say, in time from -1 to 1 or something, or in time, we'll figure out what our parameters are in times. So let's just call it from time A to time B. And the function really does look like something like this. And I'm integrating this area, except that there is that conversion factor, like we did in the integrals, in double integrals, in triple integrals. If I stretch out that line and I integrate just a straight line, there is a conversion factor, which is that length of the tangent vector. That's the conversion factor that we have to apply at each time, because that computes how different it is a piece here from a piece here, from a curved piece here to a straight piece here. That conversion factor is what this factor is calculating for you, okay, this piece here. So first of all, what I need to do is parameterize the top half of the unit circle. Okay, so from here to here, I want to I'm actually going to go like this. And we know how to parameterize a circle. What's a parameterization of the circle? Cosine t, sine t. That would parameterize exactly how I wrote it, starting from time 0. And then I want to go all the way to -1, 0. So I have to go all the way to the t's here are actually parameterizing angles. So from here to here is time t is the angle that I have done in radians. So I have to go all the way to pi. Okay? All right. So that is r of t. And then just this, remember, like what is going to happen in the formula is I'm going to take my function, evaluate at the points on the circle, times the length of the tangent vector at each point. So I actually have to, once I have parameterized, parameterize, 2, compute the length or compute the actual tangent vector. The tangent vector will be minus sine t cosine t. Okay, this is the tangent. Now compute the length of the tangent vector. The length of the tangent vector will be the square root of the square of the coordinates. Which is the square root of sine squared t plus cosine squared t, which is just the square root of 1. So this is actually just 1. So that conversion factor in this case is just 1 to 1. So I don't have to, I can just switch my integral in S is actually just going to be an integral in t from 0 to pi. Okay? So now I can just integrate. I'm going to integrate over that path the function 2 plus x squared y ds. That is going to be the integral in t from 0 to pi of 2 plus, I do have to convert that r of t is x of t, y of t, and my x is just not any x, are x values on the circle, and that is cosine t sine t. So x squared is cosine square of t times y of t, which is sine of t, dt. Actually, let me write 1 here times 1 times dt, where this 1 is conveniently the length of the tangent vector, the length of r prime. Okay? So it's just a 1. And now I just have to integrate this. On one hand, I have the integral of 0 to pi of 2 dt. That's going to be easy. And then the integral from 0 to pi of cosine squared t times sine t dt. But for this second one, I'm going to use u is cosine t, a u substitution, so that du is minus sine t dt. Okay, and that is when, by the way, that is the limits when t is 0, the cosine of 0 is 1. When t is pi, the cosine of pi is minus 1. So this integral becomes, let's just do this one, this is just 2 pi, plus, and this integral is going to become the integral from minus 1 to 1 of u squared du with a minus sign in front. Okay. So now I keep going. This is 2 pi, and then minus u cubed divided by 3 between minus 1 and 1, which is going to be at the end of the day. This is this piece is 2/3, so I get 2 pi plus 2/3. I got let me fix this because the times. So this is actually the integral at 0 is 1. So the integral is weird that it goes from minus 1 to 1. And this piece is also equal to plus the integral from minus 1 to 1 of u squared du. So it becomes a plus between minus 1 and 1. And that will be 1/3 minus minus 1/3, so it's 2/3. But the interesting part and the new part is this integral that I have. I'm integrating a function along a path using this piece here is ds, which is the parameter arc length, what we call arc length. Okay. All right, let's do another problem. I'm going to integrate the function 2x, but I'm going to do it now in there's a path that is defined in 2 different segments. Let's see what that means. It goes from 0, 0 to 1, 1 using a parabolic motion from here to here. And then from 1, 1 to 1, 2, this is 0, 0, this is 1, 1, and then 1, 2, just using a straight line. Okay? When we do integrals in sections that are defined by very different functions, we can just split the integral. So this whole path is really an integral over two different paths, and the integral over this path of 2x ds will be the same as the integral over the first path, 2x ds, plus the integral over the second path, 2x ds. Okay, so I have to first parameterize those two segments. So let's first parameterize what C1 looks like. So what are the points on C1? That is parameterized by y equals x squared. So if x is t, or y is t squared, and that goes for t between 0 and 1. Okay, those are the points on the first path. The points on the second path are going to be points that have the y coordinate or the x coordinate is fixed equal to 1, and the y coordinate is going from 1 to 2, like this. And then I can just go between t again between 1 to 2. So let's just do it easy, going from 1 up to 2. All right. So now let's find what are each one of those integrals. So what is going to be, let me actually find, so for the first path, I have t squared. So the derivative of the first vector function will be 1, 2t. And the second path is 1t. And the derivative of the second path will be 0, 1. And you might wonder at this point, what if I parameterize these paths in a different way? What if I speed up? What if I go faster than you are, and then I do that integral? Well, that's why we are parameterizing and then integrating against the length of your vectors, against the length of your tangent vectors, because if you do what I did in the parabola from 0 to 1, you are able to do it from 0 to a half, then you're going to go faster, and the tangent vectors are going to be longer. So if you're integrating in a smaller section of t, your tangent vectors that are going to show up in the integral have a larger value, and it all evens out, and the value of the integral is the same. Okay? So it doesn't matter how you parameterize. We're trying to parameterize it in the easiest way possible, so the integral is the easiest possible. But if you somehow came up with a different parameterization, the integral at the end of the day is going to be the same, except for orientation. Orientation of, it might be up to a sign depending if you go from point A to point B, or from point B to point A, which is the equivalent of, we would be reversing the integral from A to B of f of x dx, and the integral from B to A of f of x dx. They are the same up to sign. Okay, so then what else do I need here? I need to compute the lengths of these vectors. The length of the tangent vector is 1 squared plus 4t squared. So it is the square root of 1 plus 4t squared. Okay. And the length of R2 of the second one is 0 squared plus 1 squared. So this one is just 1. Now I can do the integral on each one of the paths. So what is the integral in C1 of 2x ds? That path is the first path. It's this, given by this. So I know I'm going to go in t from 0 to 1. I'm going to integrate 2x, but I have to substitute x by the values of x. So x is t. And then I'm going to multiply by the length of the tangent vector, dt. So the integral here is going to go from 0 to 1. 2x, the x coordinate is just t, times the length of the tangent vector dt. Okay? And if you integrate this, this is going to be, again, a u sub. I pick u to be 1 plus 4t squared. Du is 8t dt. So I'm going to get a factor of a 4 in there. So I'm going to get that this is also, by the way, when when t is 0, u is 1. When t is 1, u is 5, right? And I can just integrate this. This is going to be the integral from 1 to 5. Let me just do, this is going to be, let's transform it, yeah, from 1 to 5 dt, or 2 times, this is a fourth of the square root of u du. And that is even better if I write it as u to the 1/2, and then that will be a fourth of u to the 3/2 divided by 3/2 between 1 and 5, and all done and done. I get 5 is square root of 5 minus 1 divided by 6. Okay? That's the first, that's the integral in the first segment. I have a second segment to worry about, the integral about the second segment. In the second segment, the parameter that I'm choosing, I could choose a different parameter, but here it just matches that it's t is going to go from 1 to 2. In any case, I'm parameterizing this piece. And the x coordinates are just 1. The t is going from 1 to 2. And the length of the tangent vector is just 1. So I go from 1 to 2. 2 times x is just 1. So this is 2 times 1. And then the length of the vector, of the tangent vector, is 1, and just dt. So here's the integral of 2 between 1 and 2, which is just 2. So the integral over the entire path will be the integral of the first one plus the integral of the second one. So it's that. Yes. So I want to parameterize, first of all, this path. This path is described by the function y equals x squared. So if I parameterize the x coordinate, the y coordinate is given by x squared. So I'm starting with a parameterization of the x coordinate. I go from 0, 0 to 1, 1. So x is going from 0 to 1. So it's going from 0 to 1. And then the y coordinate for each one of those has to be t squared. Similarly, for this line, we have that one. I sort of like came up with it, but we do have a formula to parameterize lines from one point to the other, and we're going to use that in a moment to do something else. But in here, it's just simpler than that, because x is going, we're going from 1, 1 to 1, 2. So the x coordinate is fixed, it's always 1. And the t coordinate, or the y coordinate, is going between 1 and 2. So the y coordinate is just moving between 1 and 2. Okay? All right, let's do some other examples. In here, I'm going to just do one application of line integrals, which is for the center of mass of a linear, of a curve. So in a curve, like I said at the beginning of the lecture, you can have that the curve does not have, or the piece of cable, the piece of rope, the piece of whatever, it does not have the same density as you go along, or maybe there is some force acting on it that is changing the weight of the rope at different points. So you can figure out what is the total mass of that object. For example, if you have a rope, if you were to build one of these like space elevators that you may have heard of, these space elevators would have some rope that is like attaching this station somewhere in space all to Earth. So the gravity pulling on that rope definitely changes. When we are talking about a rope here on the surface of the Earth, we don't have that into account if I put a rope vertically, but if I go all the way from a rope from here to the moon, sort of like what is the weight of the rope, meaning how the force is acting on that rope, it will change, and I'm going to have to do an integral taking into account all those forces. Okay, so this is such a thing in that we are going to do, in fact, the center of mass of a piece of rope. And they are given by these formulas. So the center of mass will be at x, y, and I want to compute what the center of mass is, which are those coordinates, and those coordinates are given by those two formulas, which are two line integrals. So for example, let's say that a wire takes the shape of the top half of a semicircle of radius 1. It is thicker near the base than near the top, and in fact, the density is proportional to the distance to the line equals 1. Y equals 1. So what does it all mean? We have, again, a wire that is just the top half of a radius of circle 1. So the path is like that. I'm going to do a line integral over that. So I still have to parameterize this like we did before. I can, not cotangent. I can parameterize cosine t, sine t. Again, between 0 and pi, that parameterizes the rope. But now the density, what they say is that, well, if you take the line y equals 1, the density is proportional to the distance to that line. The distance to that line is 1 minus y. This is the point xy. The distance is 1 minus y, and the density will be proportional to that, so some constant times 1 minus y. So what they're telling me is that the density at any given point is given by a constant times 1 minus y. It turns out it doesn't depend on the constant k. The constant will just eventually disappear from our calculations, but this is the density. Okay? So now I have to compute two line integrals. For x will be, again, 1 over the mass, or rather the, we're going to compute first the mass, right? Because I need the mass somehow. So let's first compute what the mass is. The mass will be the integral of the density with respect to arc length. And once I have that, and then I can compute the x and the y for the center of gravity, the center of mass. By the way, the problem is symmetric with respect to the y coordinate, with respect to the y-axis. So the center of mass, the x-coordinate of the center of mass, will have to land on the y-axis. Okay, so we'll talk about that in a moment, but that's the center of mass is going to be somewhere here by symmetry. And you can compute that integral and show that that is 0, but if you realize that there is a symmetry, then you don't even have to compute that integral. So what is the derivative? Remember that the integral will be the integral from 0 to pi of the function rho evaluated as xt, yt times the length of the tangent vector dt. Okay, so what is all that? This is the integral from 0 to pi. Rho evaluated at cosine sine. Okay, so this is k times 1 minus y is sine of t. That's rho evaluated at the xt and yt times the length of the vector, of the tangent vector. We computed that that length is 1. It's the square root of minus sine square plus cosine square. Is sine square plus cosine square equals 1. Square root of 1 is 1. So the length of the unit of the tangent vector is 1, and then dt. So if you do this integral, that is just the integral of k minus the integral of k sine t between 0 and pi. So you do that integral, and the answer is k times pi minus 2. That is the mass of the rope, of the wire. Okay? And now I compute the two moments, the center of mass, the x coordinate and the y coordinate. Let's set up both. So the x will be 1 over the mass. The mass we calculated to be pi minus 2. Integral. I'm doing a line integral, but this time is of the function x times the density. The x is cosine t times the density evaluated at x and y. So this is times 1 minus sine t times the length of the tangent of the parameterization, which is 1, times dt. And t, the time, is between 0 and pi. And this, you can compute this integral if you want, but again, by the symmetry of the problem, because we're looking for a center of mass, there is just as much mass on this side that there is on this side. So the center of mass has to land on this line. You can compute this integral if you want and show that this is a 0. Let's do, though, the y coordinate. So the y coordinate will be, again, 1 over the mass, k times pi minus 2, 0 to pi. Now it's y times density. Y is sine of t times k, 1 minus sine of t dt. There's a times 1 there that I'm not writing because the length of the tangent vector is still 1. So this is, you see that this k and this k will actually cancel out. So you see that now the answer doesn't depend on the k. And it is 1 over pi minus 2 integral of sine of t minus sine square of t dt. Okay? This integral, sine of t is immediate. For the integral of sine square of t, remember that the sine square of t is 1 minus the cosine of 2t divided by 2, and that is immediate with a small u substitution. So you do this integral, and the answer is, at the end of the day, this is 4 minus pi divided by twice pi minus 2. Okay, so the center of mass is at the point 0, 4 minus pi 2 times pi minus 2. That's it. How did I figure out that that was the density? So they're telling me that there is a linear density, and it is proportional to the distance from the line y equals to 1. Proportional means that it's a constant times, so it's a constant times the distance of the point to the line y equals 1. This line over here is the line y equals 1. The distance from a point to the line is 1 minus y. So it's proportional to the distance to the line y equals 1.
So is that the density, that's the density of the curve, not the line, right?
That is the density on any point and on the wire.
And the wire is then the orange or the green?
The orange. On the orange. This function gives you a density in the entire space, in the entire plane, right? So when I evaluate it at points in here, that's what happens when I plug in x and y of t. So this is the density at time t. So if I at time t denotes an angle from the x-axis, and at time t, that is the density at that point. All right. Two different line integrals that we also do is that sometimes we are adding, instead of just adding the contributions in the entire curve of the arc length, we switch it and just look at trying to add all the possible contributions of how much the x coordinate has changed from point A to point B. Okay? So if you think of arc length, in arc length we have the integral of the square root of x prime squared plus y prime squared. So if I don't care about what's happening in the y, so I'm just forget about the contribution of y equals 0, then I would be integrating the integral of the square root of x prime squared, so it's the contribution of x prime. So when we differentiate in a line with respect to x, we're just looking at the contributions of how much the x coordinate has changed times the whatever function we are measuring against. So it changes in this parameterization or in this parameter, we are just doing the derivative of x times dt. If we're looking for the contribution from the y coordinate, from the changes in y, then we do the same, but just with y prime dt. Okay? So these are, we used to have the integral of c of f of x, y with respect to arc length. That was the integral of f of x of t, y of t, times the entire contribution of the tangent vector, so x prime squared plus y prime squared dt. And these ones are the contributions. The line integrals with respect to x are just taken into consideration, contribution in x, the contribution in y. When we have an integral, these integrals will show up from here to the end of the class. What do we mean by this kind of integral? Well, we mean one of these. We're integrating some function with respect to x, some function with respect to y. So these integrals are those. Sometimes you'll see it written like this, and this is sort of like a shorthand. And it is a shorthand because this is an integral sign, but with two different differentials. We're integrating with respect to two different things. So when you write an integral like this, we first convert it to this type of integral. This integral we're going to convert to this integral. This integral we're going to convert to this integral, and then compute. Okay? These type of integrals are going to show up, for example, when we study something called Green's theorem. Okay, so let's try to evaluate one of those. We're going to evaluate y squared dx plus x dy, where c is the line segment from minus 5, 3 to 0, 2. So what is, first of all, where is that path from 0, 2 to, minus 5, 3. That's not going to fit here. Let me write it sort of like this, and then 1, 2, 3, 4, 5 in negative, 1, 2, 3 in negative, and 0, 2. So we're going to go from minus 5, minus 3 to 0, 2. So this is our path is going from here to here. Okay, that is the path C. And now I have to parameterize that path. This is what I was talking about before, that we have a formula for that. If I want to go from a point P to a point Q, then I can just start with, so if I'm going to from P to Q, I can start with 1 minus T P plus TQ. And you can see that in this formula, at t equals 0, there's no q, I'm at p. And at t equals 1, there is no p, it's all q. So this path between 0 and 1 takes me from p to q. Okay? So whenever you have 2 points, you can use this formula, and you can travel from a point to another from times 0 to 1. So what is this formula? This formula is 1 minus t. The point P is minus 5 minus 3. And the point Q is 0, 2. Okay. So this is this formula is going to be minus 5 plus 5t plus 0, and then minus 3 plus 3t plus 2t. So this is minus 5 plus 5t, and then minus 3 plus 5t. Between 0 and 1. Okay. I'm going to need my x primes and y primes, so I need the derivative. What is the derivative of this path? With respect to the derivative of x with respect to x is just 5, and with respect to y, it is just 5. So not very exciting. Okay? So that means that when I'm integrating in dx, dx is x prime t dt. By that I mean what appears in this formula. This is what we call dx, and this is what we call dy. Those are the new differentials we're using in here. So dx is x prime t dt, which is x prime is 5. So dx is just 5 dt. And dy is y prime t dt, which, by the way, is sort of like just the chain rule. And that is 5 dt. Now I'm ready to transform my entire integral using all these elements. I can figure out what the formula is for the integral. Any questions on the parameterization? Yeah. You can do a different parameterization. Your parameterization that I just said actually might make things easier than what I just did, because I think the x coordinate is going to be easier. It might actually make your life easier to do a different parameterization. I'm using this parameterization because it works every time from point P to a point Q. We're going to see in a moment, or next time, that we are going to do these integrals also in 3D. And I want a formula that works also for any points in 3D, that gets you a parameterization without thinking much. But what you just said is actually makes sense, to take t to go from, I assume you were saying, t would go from minus 5 to 0, and then figure out what line that is, and you find what the y coordinate has to be to match that line. Perfect. That works. And as I said, these integrals are very clever in that what you're doing, you're going from t equals minus 5 to t equals 0. So your parameterization is taking 5 seconds to get from point A to point B, or from point P to point Q. In my parameterization, I'm taking 1 second to go from 0 to 1, but I'm going faster, and my derivatives are going to be bigger. my tangents vectors take into account my speed. My tangent vectors are going to be bigger. So even though in my integral, I'm going to integrate from 0 to 1 dt, you're integrating from -5 to 0. My derivative is going to be larger and is going to compensate so the solution is the same. Okay, so you can parameterize in different ways, and sort of that's why we integrate with respect to this derivative, because the derivative is taken into account what is the change of variables. It's this derivative that we're computing here is the equivalent of the Jacobian that we saw in 2D and 3D transformations of integrals. So it's doing that role so that the integral is the same when we do this change of variables. Okay, so now I can do my integral. So the integral in over c of y squared dx plus x dy with respect to the parameterization it shows is going to be, as I said, my time goes from 0 to 1 in dt. My parameterization, though, I have to write it somewhere. I have to remember it. It was -5 plus 5t minus 3 plus 5t. And y squared is -3 plus 5t squared. Dx, remember, it was 5 times dt. Here, the tangent vector did have a non-trivial x component, or x change of rate, plus, I can actually not write the dt quite yet. This is going to be plus. And then in x, that's -5 plus 5t dy. And dy was also 5 dt, so also times 5. And now the dt applies to everything. Okay? If you simplify all of this, what you get is actually the integral of 20 minus 125t plus 125t squared dt. It's just a polynomial. So you do your integral, and the answer that I get is -5 divided by 6. All right, let me, any questions about this one? Any other questions about how I interpreted this integral, dx and dy? Let's do the same integral, the same function, but now I'm actually taking a different path. So now I had 1, 2, 3, 4, 5, 1, 2, 3, 0, 2. I'm still going from here to here. But now they tell me that 4 minus y squared, x equals 4 minus y squared, actually passes through both. What does this one look like? First of all, is this even true? When y is 2, x is 0. And when y is -3, 4 minus 9 is -5. So this is true. And this parabola, it's in the y direction. So this parabola, it looks something like this. Okay? So now I'm going to go in this path. So how do I parameterize that path? I'm going to do, how do we parameterize this? The y coordinate is going from here to here. The y coordinate is going from -3 to 2. And once I know what the y is, then this tells me what the x is. So my parameterization of this motion is going to go, I'm going to parameterize the y coordinate between -3 and 2. And once I know that, the x coordinate is 4 minus t squared. Okay? What is the derivative vector? The derivative vector, the tangent vector, is -2t, 1. So that tells me that the differential dx is x prime times t. So this is -2t dt. And the differential with respect to y is y prime, which is 1 dt. So it's just dt. So now I can interpret my integral. The integral of y squared dx plus x dy is going to be the integral from time minus 3 to time 2 of y squared. Y in here is just t, so this is t squared dx. I have to multiply by minus 2t dt, so I have to multiply by minus 2t plus x. The x coordinate is 4 minus t squared times dx. Times dy, but dy is 1 dt, so it's just dt overall, like that. Okay, this is the integral from minus 3 to 2 of minus 2t cubed plus 4 minus t squared dt. And that is just a polynomial, so let me just tell you that the answer is 245 divided by 6. Beautiful number. Okay. So it doesn't match. We did a different path before. From here to here, in this path, the answer was minus 5 over 6. I went in a different path. The answer was 245 divided by 6. That's because I'm taking a completely different path. The functions that I'm integrating along those paths change value accordingly to the points I travel over. So those do not have to be the same number. We will get to that. So the values of each integral, of each line integral, they do not agree, but there will be a double integral, but somehow this integral will be related to a double integral of some other function. So we'll get there. That's what Green's theorem will tell us.
So what does this integral actually represent? What do these two integrals rather actually represent?
In this case, I've just picked some two random functions, and it's just integrating some function with respect to dx. So it's computing how x is changing in that path, how much y is changing in that path with respect to that function. So at this point, it doesn't represent anything. We'll see that there is an application of this, as you said, to compute areas of complicated regions. Instead of doing a double integral, we're going to do line integrals instead. And that switch is what theorems like Green's theorem will tell us how it will give us a use to these integrals.